Hello, everyone. My name is Hanyang, a student from New York University Abu Dhabi, and I'm very pleased and excited today to be presenting at the 9th undergraduate research competition. So our research project is on organic ionic plastic crystals, which is a new candidate for solid-state electrolytes. So our contemporary society is facing transformation of energy structure and also renewal of large and electrical equipments. And according to the International Energy Agency in 2021, 45 billion USD was allocated to renewables, and sales of electrical car vehicles reached 6.6 million, tripling their market share from 2 years before. And one of the key technology that is required to develop a more safer, more energy efficient, and energy dense energy storage system or electrical car vehicles and consumer electronics are actually batteries. And there are many types of batteries. And however, their important parameter that needs to be considered is actually the energy density. So larger energy density means that same amount of energy can be stored while weighing less or being smaller. So from this figure here, you can see that compared to lead acid, nickel cadmium, and nickel metal hydride, lithium ion battery has the smallest size and the lightest weight, meaning that they have the highest specific and volumetric energy density. And this is desirable because it will enable us to supply energy for a longer period of time. However, these lithium-ion batteries also have drawbacks. There has been many incidences that has been reported about their explosions. So panel A shows a battery that has been exploded due to the battery self-ignition. Tesla Model S caught in fire in panel B. And C shows an aviation that has been caught in fire due to the lithium-ion batteries. And D shows the explosion of a battery warehouse. So what is the component in a battery that is causing such explosions? So let's look at this very simplified version of a battery with their cathode, electrolyte, and the anode. And it's actually this electrolyte which allows the transfer of ions between the cathode and the anode that is responsible for the thermal stability of the batteries. So in conventional lithium-ion batteries, flammable organic solvents such as ethylene carbonate or dimethyl carbonate has been used. And these liquid electrolytes have caused leakages, explosions, and ignitions. So recently there has been tremendous research in order to remove this liquid electrolyte and replace them with solid-state electrolytes. And organic ionic plastic crystals, or OIPCs in short, is a new candidate to be used as this solid-state electrolyte. So organic ionic plastic crystals are made up of combinations of cations and anions that are bound strongly enough to maintain the long-range crystalline lattice, but allows local molecular reorientation. And in this table here, it shows different types of cations and anions that has been reported in literature. And depending on the type of cation and anion, the physical and chemical properties of the OIPCs can be significantly changed. And in our research project, a new material, HDMS, TFSI, was synthesized and characterized using various analytical techniques. So first was the thermal analysis. So in panel A, you can show, it shows the results obtained from thermogravimetric analysis. And it shows that the decomposition temperature of this material is high as 350 degrees Celsius, and it fully decomposes around 390 degrees Celsius. And this is a very high decomposition temperature compared to many other OIPCs that have been reported in literature. And also it is very desirable to have a high decomposition temperature and a high melting point in solid-state electrolytes because it shows that they are thermally stable. And accordingly, the DSC measurement was performed to detect the order to disorder solid-solid phase transition. And the result is shown in figure B. And the plastic phases are actually where the materials show local orientational and dynamic disorder that allows fast ion transport. And for practical usage, it is desirable for this plastic phase to occur around room temperature. And our sample showed this plastic phase after 45 degrees Celsius. And then powder X-ray diffraction was conducted in order to confirm this phase transition. So it showed that the material experiences structural changes with increasing temperature, and these changes appear to be gradual over a wide range of temperature, yet showing a very drastic change between 40 to 50 degrees Celsius, where the order to disorder phase transition takes place. And then the ionic conductivity of the material was measured. And the ionic conductivity is actually one of the most important parameters. So the ionic conductivity of the neat or the pure sample and the 5% dope sample is shown in this table here. And you can see a 5-fold increase in the pure sample after the phase transition temperature of 45 degrees Celsius. And this is due to the fact that the sample shift from a more rigid phase to a more disordered plastic phase. And then also in the 5% dope sample, you can see that the ion conductivity is higher than the pure sample at room temperature, and also it increases with increasing temperature. So it is hypothesized that the pure sample increases ionic conductivity as it moves from a more rigid phase to a disordered plastic phase. And for doping, it increases the number of diffusive species and increases number of vacancies, leading for more ion conduction. And also these ionic conductivities shows possibilities of incorporating this material as solid state electrolytes, because the current liquid electrolyte has ionic conductivities of 10 to the negative 3, 10 to the negative 2 Siemens per centimeter, and 10 to the negative 3 Siemens per centimeter is actually required for practical usage. And finally, the dynamics of the cation and anion was studied by using solid state NMR. So panel A shows the results obtained from proton solid state NMR without magic angle spinning. So you can see that at lower temperature, 293.15 Kelvin, the spectrum is very broad and featureless due to anisotropic NMR interactions and lack of motional averaging. But as you can see, with increasing temperature, the peaks gradually narrow, and the appearance of a well-resolved peak around 1.3 and 3 ppm indicates the presence of dynamics, which can average the anisotropic NMR interactions. And then looking at figure B, it is a carbon-13 NMR, solid state NMR, without magic angle spinning. And again, at 293.15 Kelvin or 20 degrees Celsius, the spectrum is very broad and featureless, again, due to the anisotropic NMR interactions and lack of motional averaging. But with increasing temperature, you can see that the peaks are very well resolved. And from this, we can conclude that the cation and anions are dynamic, and they are averaging the anisotropic NMR interactions. So to conclude, in this research project, a new type of OIPC was synthesized, namely HDMS and TFSI, and higher thermal stability and ionic conductivity was observed compared to many other OIPCs that have been reported in literature. And the plastic phase transition order to disorder have been observed at 45 degrees Celsius, and the cation and anion dynamics was studied using solid state NMR. And these analytical techniques and the results show the potential of using this new material, HDMS TFSI, as solid state electrolytes in lithium-ion batteries. And our future research will focus and aim to test their charging and discharging cycles with incorporating this OIPC as a solid state electrolyte when assembling the battery. And that's it. Thank you very much for listening.